Hi everybody, welcome back to the Feynman technique. I know I haven't been posting very many videos lately. That's due to two main reasons. The first being that I've been focusing most of my time on, most of my free time on my Understanding Feynman Integration textbook. The second reason is I've pretty much covered all there is to cover on the technique that I set out to teach when I started this channel. I mean, if you watch every video and understand and can follow along every video on this channel, then you can teach Feynman integration to other people. So there's really not a whole lot more to do as far as Feynman integration is concerned. The examples on my channel cover almost everything. I might have left out a few things. I didn't really delve that deeply into the general Leibniz rule for differentiation under the integral sign. That is the version where the bounds of integration are not constant. But usually Feynman integration deals with the case where the bounds of integration are constant anyway. So yeah, I'm pretty much done with that. I will eventually make a second channel that's going to basically be a redo of this one, only cleaned up a little bit. It's going to be more professional looking. I'll probably have like a microphone on, and there'll be better lighting, and it will be in a more professional setting instead of just in a back room in my house with a whiteboard screwed to the wall. But anyway, I saw this integral on the channel Mathematics MI with the title Impossible ? Or maybe it was Impossible Integral ? But anyway, the answer is no, it's not impossible. He solved it by generalizing it. I think he just replaced I with A and this I with B, and then generalized it and then plugged in I and I think. I honestly didn't watch it all the way through because I found a much easier way to do this particular problem without generalizing it. And once you recognize this, then it becomes really easy. Of course, I know that this could also be e to the 5i pi over 2 and e to the 9i pi over 2, but for our purposes, we'll just consider this to be true. So once you recognize that and replace this base of I with e to the I pi over 2, it becomes pretty easy. So we'll have the integral from 0 to infinity of e to the I pi over 2 times ix squared. So of course, the I and the I will multiply together to produce a negative sign. And then we'll have minus pi over 2 x squared dx. And now it becomes very easy. We'll let x equal the square root of 2 over pi. Basically what I'm saying is that u is equal to the square root of pi over 2. I'm sorry, there should be a u here. And therefore, dx is going to be equal to the square root of 2 over pi du. All right, let's rewrite our integral. Our substitution will not change our bounds of integration. This will still be the integral from 0 to infinity, and then we'll have e to the negative u squared. That was the whole point. And then our dx becomes square root of 2 over pi du, recognizing that this is simply half the Gaussian integral, which is equal to the square root of pi over 4. This becomes the square root of 2 over pi times pi over 4. Those cancel. This becomes a 1. This becomes a 2. That's equal to the square root of 1/2, but we don't like it expressed that way. Most math teachers would prefer that you write it like this, because radicals in the denominator are bad. So anyway, there's the answer. Done slightly easier than and I think that he did it. It's neat to generalize it, but unnecessary in this case. But anyway, that's the answer. Hope you enjoyed that.